So theorem 5 is that a tangent is perpendicular to the radius. And so there's the diagram of the theorem. OP, P is the point where the tangent touches a circle, and there is a right angle formed between the tangent and the radius. That's the theorem and it's true, but I'm going to run through now and talk to you why it's true. Why not have any sound? No, it's on. And we're going to do that by a proof by contradiction. So a proof by contradiction starts by assuming that the negative is true, the negated statement is true, and that is that T is not a right angle. So that point where it touches a T is not where the right angle is. So instead we assume that there is some other point that creates a right angle there. So I'm going to call that point S. And I'm making the statement, let angle TSO equal 90 degrees. So there's a right angle there somewhere, but it's not at the point where the tangent touches the radius. If I make that statement, then I'm forming this triangle. Looks like this. That's T, that's S, and that's O. And that will mean that the length of TO is greater than the length of SO, because TO is the hypotenuse. Can we see that? So then we know that. But the problem we have is that if we zoom in, and it's not a great diagram, but if I imagine if I took S out a bit further, you'll note that TO is actually the radius. And S, the point S, is a radius and a little bit more. So it's not as clear as S, but if you go down here, S is the radius to the edge of the circle plus a touch more. So we're making the statement that if S forms a right angle between the tangent and the centre of the circle, then TO must be greater than TS because of Pythagoras theorem or because it's a hypotenuse of a triangle, of a right angle triangle. But we also know that TO is equal to the radius and SO is equal to the radius plus some extra value, plus some extra little tiny bit, where X is this little tiny bit in here. And so SO must be greater than the radius. We can see that in our diagram. SO must be greater than TO, which is a contradiction. We made the statement clearly earlier that TO must be greater than SO if TO is not at right angles. So I'll just summarise that very quickly again, because this is a good practice of contradiction in chapter 8. So to do a proof by contradiction, we start by assuming that the opposite statement is true, the negated statement. So we say, okay, well, if OTQ is not a right angle, well, there must be some other point that forms a right angle. We'll call it S, and we'll make that a right angle. So OSP is a right angle. It creates triangle TOS, where OST is a right angle, and therefore TO is a hypotenuse, so it's longer than SO. We made that statement there. So that all follows logically. Then we say, well, if it is longer than SO, we also know that TO is the radius, and SO is the radius plus a little bit more. So SO is greater than radius, which means it's greater than TO, and SO can't be greater than TO and shorter than TO at the same time. So there's a contradiction in our assumption that the negated statement is true, and therefore the original statement must be the true statement. That makes sense? It's a really good example of a proof by contradiction, and it shows that this is true. So you do have to memorise all these circle theorems, but most of them aren't too bad. So you look at a diagram, if it comes from the radius to the tangent, it's a right angle. The biggest problem I see, though, is that we might look at this and go, oh, here's a chord, and then just go, oh, there's a line that's in the circle and it meets the tangent, that must be a right angle. But that's not true. It has to be through the centre. That's the only time it's a right angle, so just be careful of that. It does create lots of opportunities where you have a diameter and a triangle within a semicircle, and you end up with a nice right angle just here and another right angle just there. And you can do lots with that. And that's based on circle theorem 3 and tangent theorem, which we call theorem 5. This is an arbitrary list of theorems, by the way, so in some textbooks it won't be called theorem 5, it'll be theorem 7 or whatever. So just be aware of that. Here's theorem 6. Two tangents from the same point are equal in length. So we've just done theorem 5 where we've shown that they're right angles. I'm now making a statement that RS equals TS. So that's what the theorem is. And it's a pretty easy one to prove. So we're making a statement RS equals TS. And this is because OR is equal to OT. They're both radiuses. And also that OS is a common. So that's common. Don't know what I'm doing there. Is common. So OS is part of both triangles. So this length is equal to this length, and that length, which is the hypotenuse of both triangles, is the same length. Then if we just do some simple Pythagoras theorem, we get that RS must equal RT. It's right at the full proof, but you don't really need to. It's fairly logical from here. But we get RS plus OR equals OS, and they're all squared. That's number one. So that's from the top triangle. And we also get that TS plus OT squared is equal to OS squared. That's from the bottom triangle. Therefore, I can make both left-hand sides equal because the right-hand sides are the same thing. So we get therefore RS squared plus OR squared equals TS squared plus OT squared. But OR and OT are equal. They're both radiuses of the circle. So we get RS squared plus the radius squared equals TS squared plus the radius squared. Therefore, RS squared must be TS squared. RS must equal TS. So that's the full proof. And you see, I haven't really skimped out on my lines of working here, which is that's where the elegance comes from. Don't skip too much. But that's the reasoning there. And I won't ask you to redo this reasoning, but I do want to show you the reasoning. That's the difference between you doing methods of general and you doing maths specialist. I'm going to show you the reasoning every time. Max, you have a question? Okay, cool. There's quite a few different ways you can do this one. So you can do similarity as well. Yeah, there's more. I'm sure there's more. There's always more. You could probably use vectors and vector proof as well. Anyway, so that's the second one. So we've got tangent and a radius make a right angle, and we've got two tangents from the same point are equal in length. The third one is probably the most important. It's called alternate segment theorem. It looks a bit more complex, and the proof is a little bit more complex. This is the last tangent theorem that's important. There are quite a number of theorems. This is the last one. I'm just trying to make a bit more room. I'm struggling. There we go. Okay, so this one claims that an angle between a tangent and a chord here is equal to the opposite angle in the triangle that's formed from the same chord. So, actually I've got the wrong bit there. So this angle here in the diagram is equal to this angle here. So, and it's true for any triangle that's formed. So if the triangle's out here, it would be equal to that. And we know that from theorem 2, because these two angles are the same arc. So they're equal. This is equal to any angle formed off this arc. And that's alternate segment theorem. And I'm going to show you the proof for that now as well. And the proof is fairly trivial, but it comes from, we have to create the connection between each of these angles on the same arc and this particular triangle that's in a semicircle. Otherwise, it doesn't work. I don't actually remember all these proofs, which is why I've written these little cribs, like how we do the proof. So let's see if this falls in place. We want to show that angle X equals angle Z. So required to prove that X equals Z. And I'm going to do that by first making a couple of statements. So the first statement is that angle RST equals 90 degrees. And this is angles in a semicircle. And angle RTQ is also equal to 90 degrees. This is the angle between the radius and the tangent. So that's theorem 5 we've just done. Theorem 3 and theorem 5 give us that. So I've got a right angle here and I've got a right angle here. And therefore, X plus Y is equal to 90. So X is equal to 90 minus Y. And that comes from this area. But also within the triangle in triangle RST, we get Z plus Y is equal to 90. So Z equals 90 minus Y. Therefore, Z is equal to X as required. So that's just a link between a right angle triangle inside the circle and the right angle created between the radius and the tangent. And X can be linked to Z via Y. Now, once you've linked X to Z, well, you can link X to any other angle that's the same as Z. So any angle that comes off chord TS is equal to Z. So that is the angle at R, the angle at X, and this is from theorem 2. The angle over here, which I'll call the angle at A, that will also be Z. They're all Z. So X is equal to Z, so X is equal to any opposite angle in the triangle that's formed off the same chord. That's alternate segment theorem. And think about why it's called alternate segment theorem. So this is X, it's off a chord that creates a segment. X and the alternate angle in that segment. Alternate segment theorem. That's it for today. That's it for the tangent theorems. So example 6. I'll run through just a couple of examples. No, but that's the link to prove it. Okay, so you see how X equals Z in triangle ATS? AT is not perpendicular to the tangent, nor is TS. So there's nothing perpendicular to the tangent, but it's still an alternate segment. We just need to create that RT diameter to create the proof. And, again, there are other ways to prove this, where you don't need that semicircle, but that's the easy way, or one of the easy ways.
So even if you don't have the PQ, then have T, it still work?
Well, you do need X is between ST and TQ. So you need that line to define X. The X is between the chord and the tangent. But what this does, the 3 theorems you've seen today link tangents into the circle. So there's now a connection between any tangents and the circle. Okay. So example 6, find the value of X. And we're given 120. I'm going to, and I'm expecting most of you will do this as well. This is the way I'll approach this question. I'm going to ruin my diagram by drawing all over it. You might choose, you've got to use a blue or black pen, but if you want to, you can take a pencil with you and ruin your diagram in pencil. It's not really the bit that will be marked, and it means that you can reuse your diagram if you want to. So that is something to consider. But if I do this, I can see that this angle here is a right angle, because that's a radius and a tangent. Therefore, I can work out that angle, because so that will be 70. This is 90. If this is 90, I can probably work out that angle. Not sure. But either way, 70 is there. So I can work out this angle is 110. Does that help me? It does, because this is a triangle in a semicircle, so that's 90. So I've got 90, 110, and 100, and this is a quadrilateral here. So I can see I can work out X from that quadrilateral. Does that make sense? So I've done that mapping now. I've mapped out how I'm going to do it. I'm going to do it by going, this is a right angle. And then I'm going to do it by saying, if that's a right angle, this is 70. If that's 70, this is 110. Because that's 110 and this is 100 and this is 90, so that will be step 4, I can now work out X. And what I'm going to do now is I'm going to write my reasoning up better. So I'm going to rub all that out. It's on the video, if you want to have a look at it. And I'm going to do some labeling. I'll call this T because that's tradition. I'll call this S because that seems to be traditional, P. And I'm going to call this A, B, and C, because once tradition's over, I can go back to the start of the alphabet. And my solution will be angle STO equals 90 degrees, and that is the angle between tangent and the radius. That's my first solution, my first statement. My second statement will be angle SOT equals 70 degrees. This is the angle sum of triangle SOT. So I've just used the angle sum. and the angle sum's 180, so 20 plus 90, 110, 70 degrees left. And then I'm going to say angle BOC is equal to 110 degrees. This is angles on a straight line. And then I'm going to say angle TAB is equal to 90 degrees. This is angle in a semicircle. And you'll note here that BT is the diameter. So angle in semicircle with BT is the diameter. And then I'm going to make the statement, therefore, x plus 90 plus 100 plus 110 equals 360. This is the angle sum of a quadrilateral. And so x must be equal to 60 degrees. That's it. And actually, the question can go further and ask you to find this angle now. That's 30. And then this angle, well, that makes sense, actually. That's 30, which means that this is 60. 60 plus 20 makes 80, making this 100. And that's vertically opposite. So it all links back together anyway. But there we go. Any questions on that? You need to practice those because you need to, like, the writing out the proof should be easy. It's defining, it's mapping your way from the start to the finish. That's the hard bit. It's really that first step that I did where I ruined that diagram to find the path I was going to follow. Work together when you do them because you'll find some people find different paths and they all work. Chris? Yeah, it will be. It's not yet, but it will be. So once you've done 10 of them, you'll find they're not too bad. Yeah.
So could you do it using theorem 7 alone by finding SBT, which is CTS, and then that would be the opposite one.
So if you can find this angle,
yeah,
then that's the alternate segment angle. Yes, you could if you can find this angle.
Yeah, you can. It's 100.
How's that?
No, it's. I meant the opposite.
You do, that's 100.
Yeah, that's 100.
And then you say, therefore that's 60.
Yeah.
And therefore that's 60.
Yeah.
There you go. You've just cut out a line of working, maybe 2. Well done. There are going to be different ways of doing it. Okay, I'll do one more with you. Example 7. Develop an alternate proof to the alternate angle theorem prompted by the diagram given. Who can map that out for me?
Is BOA 2 times?
Okay. Let's start our mapping. So firstly, that is 2 alpha. Okay, good. So that's one of our theorems. Is that theorem 1? I can't remember which one that was. So we've got 2 alpha. What else do we know? Sorry? Which one's the right angle? OBU is the right angle. Good. So that's definitely a right angle. What else do we know? No, that's what we're trying to prove. We want to show that this equals alpha. Then we're proving the alternate angle theorem. What else do we know?
Does it have to be an isosceles?
Excellent. Can everybody just log that in their mind right now? These are 2 radiuses, so therefore you have an isosceles triangle. Really common step in a proof, and it's one that you know about isosceles triangles. So I've not specifically taught you that as a theorem, which means it's one that people often forget to look for. So if you have 2 radiuses in one triangle, then it's an isosceles triangle. Just be a bit careful though. This looks a bit like that's a right angle, but there's nothing to say that's a right angle. So in fact, if anything, it looks like it's more like 85 degrees. So we know that this angle is equal to this angle. So that means that each of these is actually 90 minus alpha. 180 minus 2 alpha divided by 2 is 90 minus alpha. So if this is 90 minus alpha here, then we can show that this is alpha because that big angle was 90 degrees. Does that make sense? I know, and my diagram makes it hard to follow that. But let me show you. So let's start by saying angle BOA is equal to 2 alpha, and this is angle at center equals 2 times angle at circumference. So we know that's theorem 1. And also let's make the statement that OA equals OB, which is the radius. And so therefore, triangle OAB is isosceles. There's too many is's in this. Isosceles. Okay, good. And so therefore, angle OBA equals angle OAB, and I'm going to call them X. And therefore, you might find you get a whole stream of therefores. 2 alpha plus 2x is equal to 180. This is angle sum of triangle OBA. And that means that x is equal to 90 minus alpha, which means that angle OBA equals 90 minus alpha. Now, here's the step that some people weren't sure about. We've already made the statement. No, we haven't made the statement, actually. And angle OBU is equal to 90 degrees. This is angle between tangent and radius. And angle OBA plus angle ABU is equal to angle OBU. So that's just adding those two angles together. And I know my diagram's slightly disappearing. I'm going to zoom in a little bit so you can still see the diagram. We know OBA is equal to 90 minus alpha, and we know that OBU equals 90, and we still have ABU, which is what we're trying to find. So we subtract 90 minus alpha from 90. Angle ABU equals 90 minus alpha, which just equals alpha, which equals angle BPA as required. So there's the alternate angle theorem proven in a different way. That would be definitely, I think that would probably be a complex unfamiliar. If I asked you to do a proof based on the prompting of a diagram, then that would be definitely complex, probably unfamiliar. I've done one example with you, but every example of this would look different. The problem with this type of question is that you may just spot it straight away, but you may not. The easiest way to do a question like this, though, is if they haven't defined values, go in and define the two things that you want to prove, and then start jumping through the diagram to find other things with respect to those angles. But you don't want to get down to alpha equals alpha. You still want to do your left-hand side, right-hand side. So once you've worked out your path, start at one side, work through your path, and then show that this implies that's equal to alpha as well, and that's then an elegant proof. Rather than getting to, working from both sides next to each other and showing that alpha equals alpha. What angle? If there was a tangent at alpha at A, do you mean like that? Or do you mean this angle here? Oh, so that one there, that would have to be, see that's a curve? So we can't have a defined angle there. That would be defined by the tangent. And the answer is yes, it would be. And that's interesting because if I connect that tangent to here, we're saying this is alpha and this is alpha because both of them have the same alternate angle in the segment. And if that's alpha and that's alpha, it's an isosceles triangle, which makes sense because that means that these two are equal and the tangents from a point to a circle are equal in length. That's term 6. And there we go. Everything comes around in circles. I've got an example 8 and I've got an example 8 again, which is always good for a math teacher to have. So I'm going to leave this up on the board and then I'll also pop up the work that you've got to do and I'll do this a bit later on. So we're going to finish example 8 and example 8 for the end of the lesson.